Welcome to a new video about BJT amplifier frequency response. In this example we will discuss a similar example as we have done it in the previous video using the frequency response of the BJT amplifier. In this case we will look at the effect of the output capacitor, in this case C2. So of course we will see everything step by step in our calculations and verify these in SPI simulations. So we have exact same circuit. The one addition here is the capacitor C2 and we have a load here RL. And we assume that our C1 here is a very large capacitor that's only here necessary to keep the DC settings as we have it before. The given values are shown here again exactly as before. The only addition is the resistor RC here, and the capacitor C2 here is 0.1 microfarad or 100 nanofarads. And we have also in addition that we have an early voltage, in this case of 100 volts for our transistor, which is the BC547B. Okay, we start first with our small signal circuit for the frequency analysis, because we again need to have the following questions to be discussed. The transfer function, we also look at the maximum voltage gain, and finally we look at the lower cutoff frequency for this circuit. Now this is a small signal model or small signal circuit where you can find the analysis for this circuit, and you see that we have also included the C1 and the C2 here just for our frequency analysis. As said before, we will go with the C1, which is a very large value, in order to only capture the effect of the C2 in this example. Now, how do we proceed? We need to go all the way from the input VI to the VO, so we will do that in steps. First, we apply the voltage divider rule from the input voltage to the base, similar to actually what we have done. So from this node to this node, that's actually given by this expression. Again, we have the C1 is very large or infinite. So the ZI will be then here, which is going into the base node, that is the impedance we see, divided by the RS plus ZI. And since the C1 is infinite, we can say the reactance of this capacitor is almost zero, so we have a short here. Okay, then we apply also the voltage divider rule from the base node, so from this node, going all the way to the emitter node, that's actually shown here. So how to do that? Actually, we look here in the base node, we see here the ZIV, and we also want to calculate how much voltage we have across this resistor R pi. And that's given by the R pi divided by the complete impedance looking from this base node to ground. So what is then the value of the ZIB and what's the value of ZI? That will be discussed shortly. Then the next step is the expression of the voltage at node X, which is this node, or that node is the exact same, in terms of the voltage V pi. That's this voltage. So that's also a question mark, and that will be also discussed shortly. So Vx over V pi, all in the Laplace domain, needs to be determined. And the final one is the expression of the output voltage, which is this, in terms of the Vx. That is actually going from this node to that, and we see here that we have voltage division as a high pass filter. That's the C2 and the RL. So we have the resistor RL divided by the summation of these two, and the 1 over the SC2, which is our reactance of the capacitor C2 plus RL. And if you change this in a different, more convenient format, you get actually this one by multiplying the numerator and denominator by SC2. All right, that's actually the expression we have. We still need to go for this expression of Vx over V pi. So this is the collector current actually in this case. You see that it is a little bit different than the situation before, because we have the resistor RO here, which is our dynamic output resistor in this BJT. So normally we had only this IC here flowing here, which was then equal to GMV pi. Now it is a little bit larger because there's also current flowing through this RO, which is IO. And this current here, IC, will also go back here, so IC, and then you get here the base current. Together with this collector current here will be again making this emitter current. That will be the same, but your collector current will be a little bit larger because of this effect of this RO. What is now the value of the ZIB? Well, that is a little bit complicated, and looking here, if you don't take this RO into account, you will say as before R pi plus beta plus 1 times the RE. That's actually what you see here, but it is an approximate value. Why? Because the current flowing here is not beta plus 1 times the RE. It is a little bit different because that's the collector current, which is also a little bit larger because of this RO. So we will see here that the ZIB determination of that one will be different, and it's actually a little bit lower since the current here is larger because of this RO. But we'll keep this formula, use that, and we also know that it is not exactly as we have it here. And the impedance looking here, ZI, is then the parallel combination of the R1, R2, and the ZIB we have here, and that is given by this expression. Okay, now we continue with our determination of the Vx over V pi. That is the next step. So looking at the right side of the node X here, that is what we call the impedance Zx, and that is then the impedance of the parallel combination of Rx and the series combination of the C2 and RL. That's actually shown here. So I can then calculate that by multiplying the RC and this term divided by the summation. That's actually shown here. And then multiply the numerator and the denominator by SC2. That's shown here. And we see here now the expression for the Zx. The collector current is also shown here in the AC form. And there's also this current through RO. And we also can calculate now the voltage at node X. And that can be written like so. So we can say this voltage here is minus IC times Zx. Why minus? Because this current here is going actually in the opposite direction because we measure from this node to ground, and the current actually is coming from ground to that node X. So that's why we need this minus sign, and we have now this expression for voltage Vx. Now the current equation at node X can be written using Kirchhoff's current law. We can say this current is equal to this current plus that current. That's actually shown here. So Gm V pi plus the IO. That's the collector current. Okay. We also have this emitter node here, E. Now we can also start with that one, and we also have the base current here. So if I now also develop the equation for the current, Kirchhoff's current law at node A, E, I can say IE, emitter current, is then the base current plus actually the collector current, because these two are the collector currents, which is actually this one. And that's actually showing, because we know this is not really a new story, but it's now also written here from node E. Now the voltage at node X can be also written in a different form, like the voltage at this node is voltage across the RO, which is then using Ohm's law, this current times the RO, plus the voltage across the resistor RE, which is then the emitter current times the resistor RE. That's actually shown here. Now we can now use these equations and then sum up that to get an equation for the Vx as shown here. So we can say IC minus the IO, my IC minus the GmV pi, that is the IO, that's actually this. So we replace that by this part, and the emitter current is actually the summation of the base current, and the collector current is also shown here. Now let's bring it here and then change the IB, because this current is the V pi over R pi, again just using Ohm's law. That's shown here. That's the only change from going here to there. And we can now collect the terms where you see the IC. Now we have an IC times RE here, and we also have an IC times the RO here. So that's taken together. We also have collected the V pi term. So we have here minus Gm V pi RO. That's this one. And we also have the V pi over R pi times the RE. That's shown here. Now we can also take out the V pi here, but first we will do the following. We can say the IC here again from this expression is actually Vx divided by Zx. That's actually shown here. And then we have again the same expression, and now collect the terms by making the following step. Left side and the right side, we can now take the parts where you see the Vx, so Vx here, and this Vx will be then placed to the left side. And we have here the only part where you see the V pi's. That's actually shown here. Now, multiplying the left and the right side by the Zx and also by R pi. Now, we do that. Then we have here a Zx plus RO plus RE times the R pi outside. That's the right side, left side. exact same value the parameter we used for multiplication on the right side. So then you get here the minus GM RO times the R pi plus RE, and then outside we have ZX. Well, we were looking actually to the expression of the Vx over V pi. That's actually almost here done, because now you see the Vx and V pi in terms of the other parameters. So we can do that by cross multiplication and divide it out. And then you can see here Vx over V pi is then minus GM RO R pi plus RE in the parentheses times the Zx divided by this term. And we can also write it down in this more convenient form. And then you have now the expression we actually wanted for this situation. Okay, let's bring this here, and also the expression for the Zx, looking here to the right side of the node X. And now we can write down this expression in more detailed form using also this reactance of the capacitor, just the expression for the Zx. That's actually shown here. Now we can further simplify this, because we see here the 1 plus SC2 times the RC plus R1 in the parentheses. But it's also shown here, so we can divide it out and then get this term inside here and multiply it by RO plus RE in the parentheses. That's also shown here. So you see actually the R pi is actually there still. Only this part is going here, and then you only leave here RC times this term and also this term here. Okay. Next, we see that we can take this here in the numerator together, and the R pi can be also taken here as a multiplication, and we have an expression like so. And the final step is take the terms where you see the SC2 together and collect them, and you have now this final result. So you see here the R pi again outside, but now you see the RC times 1, which is RC, and then RO plus RE times 1, so that's actually this part here as the constant. And then you have the frequency dependent part, which is the SC2RL RC, that's actually here. And you have also this RO plus RE times the product of the summation here, that's also shown here. And we have outside that complete expression, the SC2. So that is the expression for the Vx over V pi now here. All right. So the transfer function we were actually looking for was the VO over Vi in Laplace domain. And now we can do that in steps. So we can say VB over Vi times the V pi over VB times Vx over V pi times VO over Vx. So we see now here 4 terms. If you now cross over the VB, V pi and Vx, we get actually V over Vi here as we wanted in the original situation in question A. Now substitute here the expressions for the 4 expressions, so 4 fractions actually, then you have this expression. And we also know, that's the note we already have discussed, so ZIB is approximate value, it's actually a little bit smaller. So it's not R pi plus beta plus 1 times RE, it's a little bit smaller because of the current here for the IO. We just take it here for this time as an approximation, and ZI is this expression here. Well, now substitute this expression here, you see that, and now you see the following, so we can now simplify this further. R pi will go, that's shown here. And we have here the 1 plus SC2RL will go, because that's actually also shown here. So we can now have this more convenient form. So this SC2RL will go here in the numerator. Again, we lose our R pi here, and we also lost this one. And also here made this blue, that is our zero frequency. So it's actually, we have a 0 at S is 0 actually. So the zero frequency is omega Z is 0. And our pole frequency is actually given by this expression, so you equate that complete denominator to 0, and then you find your pole frequency, which is then given by this expression. And now using these 2, we can determine our lower cutoff frequency. What we know most of the time that the RO is much larger than the resistors around this circuit. So we have RO much larger than the RE and also RC. So we can approximate this numerator by the RO, which is also valid here because RO plus RE is also times actually RO times this one, approximate. And this is again much smaller than this term here, so we can again leave that. And you see that we can cross over, so divide out the RO here, then you get here approximate value, changing from this more complex form into a very simple form, 1 over C2 times the RC plus RL. So we actually conclude now the following situation. Looking at this circuit, we can determine the pole frequency just looking at the C2 and the RC and RL in this form for this situation. So it's quite simple if you of course assume that the RO is much larger than the other resistors. Okay, let's continue and use the fact that we have this approximation. Now at the very high frequencies, we have also here the transfer function for our voltage gain. We know that then the term here will then dominate. That's actually the pure imaginary part. And we have here also a part which is the pure imaginary part that will dominate, and this is not dominated anymore. So we will approach actually this expression where you see here the parts, the RS plus ZI times ZIB. That's actually, we only drop out this part in the expression. This is approximate value when you approach a very high frequencies. Now, if you now also cross over this SC2 here, then you have actually this expression, which is our A max. But again, the side note, the ZIB is not exactly this, so it is a little bit smaller. So the calculated value for our A max here, or the voltage gain max, is a little bit smaller than the actual value. So we should have then a larger voltage gain because of the ZIB is smaller. So because it's also in the denominator here. So again, summary, ZIB must also include the current through RO. We haven't taken that into account, so that is an error. The actual value is then lower than the R pi plus beta plus 1 times the RE, and the error here in this case could be approximately 10%, maybe a little bit less or maybe a little low, but approximately 10% error here, but larger. So we have larger voltage gain than the equation here. Okay, let's continue now and do the analysis towards the lower cutoff frequency. There's also an alternative method which is most often used because we most of the time want to calculate the lower cutoff frequency and not really interested in the transfer function or the voltage gain. So how do we do that? Now the determination goes as so: you determine the impedance seen by the capacitor C2. What do I mean by that? Now we have the two leads here of the C2. Again, we assume that C1 has a value which is infinite farads, so this is a short for all frequency operations. And I want to know, or we want to know, what is then the impedance seen between these two nodes. So what is the impedance seen by the capacitor C2? Now, first we short the input, or we disable the input, so that's actually the VI is going to short. And this is also short, so we actually have an effective RS, R1 and R2 in parallel in series with R pi. That's actually the complete node or the branch looking from the emitter node all the way to ground here. That is the effective part here. So looking here, which I call the ZIC, so looking in the collector node input, then the associated time constant of this capacitor C2 is then given by this expression. This is a very important expression because this time constant will also determine the lower cutoff frequency. So you see the C2 and the impedance seen by the C2, which is given by ZC2. And the ZC2 is actually the impedance ZIC, which should be determined in parallel with this RC and in series with the RL. So that's actually shown here. Now we said before there is an approximate value which is RC plus RL. Well, that is the case if the ZIC is much larger than RC. That is of course true, but it's also not always true, so this is a more accurate result. So what is ZIC? Now, if you now apply here a test voltage, you can then come up to this equation, and you see here the 1 plus the GM RO. So this GM will then multiply by this RO and plus 1 times, there is then now an expression where you see the RE parallel with the branch here, which is then the R pi plus the parallel of these three resistors. You see R1, R2 and RS. And of course that is again parallel to RE. And that will be multiplied by this expression, this part, which is then the ZIC, that will be then here. Now thus we have this following time constant expression. You see here now the tau C2. Now the pole frequency then associated with this capacitor is then given by this expression. So pole frequency is 1 over the time constant, so 1 over that, and that's this one. Again, a more approximate approach because this is a little bit tedious, and you might say, okay, I need to calculate also the GM, I also need to calculate R pi, and I don't want that. That's of course most of the time the case, so you want to have a very simple and fast result. Then you can go always for the situation if the RO is much larger, then the IC is also much larger than the RC. Again, the same conclusion as before, and then you have this simple time constant, and then your lower cutoff frequency or the associated pole frequency with this C2 will be then given by this expression. Now compare this expression with that one. Of course, this is much simpler to use, and also you don't need much parameters to continue because this GM, RO, and R pi are not known yet, but here you know the values for your circuit like the C2, RC, and RL, so you can proceed much faster in this case. Okay, now let's continue and now really summarize the situation as we have done it so far. So the transfer function first, again, this is the transfer function we have determined. This was the maximum gain, again assuming that this is the case. Of course, this is the IB. And we have the lower cutoff frequency we have determined like so. Okay, now and the approximate value was this. So if you want to use it a fast result and assume the error you might have, that is the formula you can use. And this is the formula again. And now this is the formula going from this lower cutoff frequency to the in the radians per second to the lower cutoff frequency in hertz, just by divided by 2 pi. All right, let's continue and now calculate actual values. Now, before we do that, we know that we need the DC analysis. Why? Because we need to calculate the GM, we need to calculate the RO, we need to calculate the R pi and all the other parameters. So we assume first linear regional population, and that means the collector current DC is equal to beta times the collector current of the DC base current. So we actually have this R1, R2, RC, and RE again. So we lose this part because the capacitor C1 is open and the capacitor C2 is open. And then we convert that to Thevenin equivalent circuit. So this R1 and R2 and a Thevenin voltage here at this node B. And that's then given by these expressions. So the parallel combination of R1 and R2 will make this. And that will result in 16 kilo ohm using the values here. And a Thevenin voltage is just the voltage divider rule here, R2 over R1 plus R2 times the VCC. Again, the exact same procedure as we have done it in the previous example, and that will give us 6 volts. Okay, now again the Kirchhoff's voltage law for this part, and that will then result here. So VTH, that is actually our threshold, Thevenin voltage, is equal to the voltage across this Thevenin resistor plus the VBE plus the voltage across the RE. And we know that IE is beta plus 1 times the IB, and then take this together, you have this expression where you now have the IBs here together, and then you can now express the base current in terms of the other parameters here. All right, so we can now calculate the base current because we know the Thevenin voltage, we know the other parameters, so we can just substitute that here, and you get here 27.81 microamps, and the IC is just 290 times this base current. That's shown here, so it's approximately 8.06 milliamps, and then we also have the emitter current as shown here, so 8.09 milliamps. We can also do the check because we like to know what the collector emitter voltage is, so it should be above the 0.2 in order to stay in the linear region, so we need to check that because we made this assumption, but we have to also verify this. We do VCC, so we make actually the Kirchhoff's voltage law at this output loop from going all the way there, also shown here actually, so VCE. So this is it, and I would like to isolate the VCE, so this is this one, and now substitute here the values for the collector current and the emitter current and also the resistors, and that will result in 5.081, which is definitely larger than 0.2, so we can say our assumption is correct, so we are in the linear region for this circuit. Okay. Now getting back to this frequency analysis, and we use now the AC analysis to determine the cutoff frequency again. So we need the R pi, so we can do that because we have the DC base current just determined in our DC analysis. So we can do that. This is the thermal voltage, 26 millivolts approximately at room temperature. We know this DC base current, so that will result in 935 ohms. GM using this formula, again using the DC collector current, and that will result in the 0.3102 Siemens. The RO is given approximate by the early voltage over the DC collector current. Now early voltage is shown here, 100 volts, and the DC collector current is shown here, so that is then approximately 12.4 kilo ohms. And we also again look at the nodes between the C2, so these two, and we will determine now again the situation as we have done it before. So we will short this, and we also short this because the C1 is much larger than the other capacitor C2 here, so we can assume that this is a short. And looking here, ZIC, we say that this is again the time constant we need to determine, Z2 C2 times the ZC2, and that's also again shown here. And this was the formula we already have discussed, and now we can now substitute the value because we know the GM now, we know the RO now, we also know the RPi now. So these three are known. Now let's substitute that and also the values we have from our R1, R2 and RS, and that will result in 1.47 mega ohms approximately. So it is much larger than RC, so we can almost approximate that actually by this simple formula, RC plus RL times the C2 for our time constant. Now thus in this case we have the following. Calculate that will be approximately 500 microseconds, so a little bit smaller than that. So the lower cutoff frequency is then 1 over that value, so that will be then 2000.27 radians per second, so almost 2000 radians per second. And if you now convert that to hertz, so from here to hertz, you divide by 2 pi, and that results in 318.35 hertz. Okay. Now let's now go to the simulation results for the DC analysis first. This is the circuit for the DC analysis. You see some nodes here, and these are the results we have calculated, and this is the table which are showing the DC results. You see here the IB, which is this current. This is a 26.77 microamps, so close to what we have calculated. You see here the resistor RC current, so IRC, which is 8.1 milliamps, so close to what we have, a little bit larger here in the simulation than what we have. Again, because of this RO effect, so that's actually what we see here. And we also have this emitter current here, which is 8.127 milliamps. Again, a little bit larger than what we have calculated. The collector emitter voltage is actually the voltage at node 7 minus the voltage at node 3. So we need to go to the node 7, which is 9.9 volts, minus the voltage at node 3, which is approximately 4.9 volts. So it's approximately here 5 volts difference. So we see also that here in our results. So this is confirming very well. Okay, next one is about the simulation results for our Bode plot. So this is now the Bode plot for the gain only. You see indeed there is a high pass filter characteristic, so it is going up and then levels. So there's a cutoff frequency here, and there is also the voltage gain here. And that was our circuit. So the voltage gain here is approximately 2.36 or 35 dB. And we have the cutoff frequency of 318.36 hertz in the simulator, and we have calculated 318.35 hertz. So you see it's very close to what we have calculated and also seen that in this simulation result. So this is a very nice result. Alright, that was our example considering the output capacitor effect on our BJT amplifier circuit, and we have determined how we can calculate that using the small signal model. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.